Hello everyone. So in this video I am going to address a special type of series called the P series, and it looks like this, where P takes different values. So for example, if P equals 1, you get the sum of 1 over n, which is called the harmonic series. We already know that it diverges. P can take any value that is positive, and it does not have to be an integer. So P has to be a positive real value. P could be 3/2, could be square root of 2, could be 1, could be 5, okay? Could be a number between 0 and 1 or more than 1. Could be 1 as well. And so what are we going to do is we're going to depend on this famous integral, which is the area under this curve from 1 to infinity. So it's basically this area here. And we're gonna depend on that area and draw some conclusions about the series, this P series. When does it converge and when does it diverge? Now, you know, if P is 1, for example, let's focus on the area under the curve. If P is 1, you just get 1 over x. And 1 over x looks something like this, right? But in the first quadrant, it just looks like this. If P is, let's say, 2, you get 1 over x squared, which looks like that. And again, in first quadrant, it looks fairly similar to this. It doesn't sit on this black curve, but it is similar. 1 over x cubed looks very similar to 1 over x, right? So in the first quadrant, 1 over x to the some power p more than 0, they all look something like this, okay? Let me fix one arrow here, all right? And this area here is exactly the area from 1 to infinity. It's this area that I'm shading right now, okay? Now, let's look at the series itself. When n equals 1, you get 1 over 1 to the power of p, which is 1. So when n equals 1, the height is 1. So you land here. When n equals 2, you get 1 over 2 to the p. 1 over 2 to the p is this height when n is 2. So it's this height, right? And so when you add up these areas, you end up with this area under the black rectangles. Try to ignore the red shaded pieces. And you notice that the area under the rectangles is bigger than the area under the curve from 1 to infinity. And therefore, the series that I am interested in has to be greater than the area under the curve. Now, I'm going to pick the same series. I just have to move to the next line, but it'll be like a string of inequalities. If I pick the same series, but this time I'm going to add 1 to the integral. Okay, in other words, I can pull 1 from here and start at 2. Say 1 plus the sum of n equals 2 to infinity of the series. What happens is, I'm going to end up with this area here is exactly the area under the red. And I want you to think through it and see if it makes sense to you. Now, if you look under the area under the rectangles, it is an underestimation, or it is lower than the area under the curve from 1 to infinity, including 1, which means this area here under the curve starting at 0, because I added 1 here, is actually bigger than the area under the rectangles, right? So therefore, this integral plus 1, this sum here, is bigger than this sum. What it tells me is that the series that we are interested in is stuck between this integral and this integral plus 1. What does that mean? It means that if the integral converges, has a sum, I should say, if this integral diverges, the series must diverge because it is bigger than the integral term by term. Conversely, if the integral converges, you add 1 to it, it still converges, then the sum must converge as well. Therefore, the integral and the sum they both behave the same way. They both diverge or both converge. Now, if this converges to 5, it does not mean that this will converge to 5. If this converges to 5, all I have to say is this converges, period. We don't know what it converges to. And that's a concession, because it's not always easy to find the sum. So we made a concession. It's like, okay, if I can't even find a sum, if it does exist, why don't I just find out if it converges to at least, right? So that's what this exercise guarantees us, that if the integral converges, the sum will converge. If the integral diverges, the series will also diverge, okay? Now you might say, well, if this converges, why should this converge? What if it moves in the other direction? Notice that this is a series, which is a sequence of partial sums. And all sequences of partial sums with positive terms have to be increasing sequences. So this is also moving to the right, as this one is. And if this stops or converges, the one behind it coming toward it will have to converge as well. Okay. So let me just share with you a couple of examples. Not examples, just, give P different values. So here's where we are. Both converge or both diverge. So what I'm going to do is I'm going to focus on the integral and see where it converges. When does it converge? For what values of P does it converge? And if that is the case, the same thing will happen to the series. And if for some other values of P this diverges, this will diverge as well. So let's do that first. So here's my integral. And I just wrote this way. And before I integrate, I don't like infinity, so I just bring in a dummy variable u, and I let u go to infinity. So this is exactly this. This is a proper way to say this, okay? So let's integrate this, just a power rule. You add 1 to it, and you divide by that quantity. Notice that negative p plus 1 is the same thing as 1 minus p. So now I'm going to evaluate this piece from 1 to u, assuming u goes to infinity. What I'm going to do first is just pull this constant out so it doesn't bother me. And I'm just going to plug in the u, and then I'm going to plug in the 1 for x. What am I doing here? Yeah, for x. Sorry. Plug in the u for x and plug in the 1 for x. And then you're going to let u go to infinity. So I get limit as u go to infinity of u to the 1 minus p, u to the 1 minus p, minus, plug in 1, you get 1 over 1 to the power of 1 minus p, and the constant remains outside. Okay, I just took it outside. Now, this is just 1, so I just put it there. So now I can pause and draw some conclusions quickly. If this limit here is a number, it's some value, when you subtract 1 from it, it's still a real number. And when you hit it with 1 over 1 minus p, assuming p is not 1, you just get a number. Conversely, if this limit is infinite, and you subtract 1, it's still infinite, and you hit it with a constant, it's still infinite. Make sense? So, how do I know where does this go to? Well, it depends on the sign, SIGN, of the exponents. So if 1 minus p is negative, saying basically that p is more than 1, if p is more than 1, which is this, that has to go to 0. The so-called infinity to some negative number, I hate to write infinity like this, to some negative number is the same thing as 1 over infinity to some positive number. Make sense? This is a bad way to write mathematics, but I'm just trying to visualize it for you, which means that this goes to 0. Okay? So what does that mean? It means that if p is more than 1, this limit is 0. Well, 0 minus 1 is negative 1 times a constant. It's a constant. I know it is negative 1 over 1 minus p. I really don't care. I just know that it is a real number, which means the integral will have to converge. So if p is more than 1, the integral must converge. And if the integral converges, what happens? The series must converge. Conversely, let's look at case 2. Let's assume that 1 minus p is more than 0, which also means that p is less than 1. P is less than 1. The same thing as saying that p is less than 1. Notice p is more than 0 because we said it early. So if p is between 0 and 1, which means the exponent is positive, then this blows up, right? infinity to some positive number blows up. So that's infinite. Subtract 1, it's still infinite. Multiply it by a constant, it's still infinite. Notice P is not, we're assuming P is not 1, okay? I'm going to deal with the case where P is 1 separately. So that means if 1 minus P is more than 0, or say P is between 0 and 1, then the integral must diverge, which also means that the series must diverge. They both converge or both diverge. So, quick summary. If P is between 0 and 1 non-inclusive, I'll deal with 1 separately. If P is strictly between 0 and 1, we know the integral converges and therefore the series must converge. If P is more than 1, then the integral converges and therefore the series must converge as well. Make sense? Now what happens when P is 1? Now you don't want to look here. When P is 1, you've got a problem on many levels. You can't raise the so-called infinity. Remember, you don't want to write infinity. I'm just talking out loud so you can visualize the problem. If you have infinity to some power 0, I don't know what that means. Also, you have 1 over 0. That is another problem. So what you want to do, if P is 1, you don't want to do any of that stuff at all. You could simply go back here and force P to be 1. So you'll end up with an integral of 1 over x dx. When you know that is natural log of x. Positive x, you don't need absolute value because x is going from 1 to infinity. Well, natural log of x, let me write it down. The integral of 1 over x from 1 to infinity is natural log of x from 1 to infinity, which is limits as u go to infinity of natural log of x from 1 to u, which is natural log of u limits as you go to infinity minus natural log of 1, which is 0. Well, that is infinite, isn't that true? So when P is 1, the integral diverges. Isn't that true? Well, if the integral diverges, so as the sum, the series must diverge as well. If P is 1, this diverges, therefore this must diverge. Another way to look at this is, if P is 1, don't even look here. If P is 1, you get the harmonic series. And you know that harmonic series diverge, because we proved it, okay? So what does that tell me? Why do I care about P series? Well, let's just pick a few values of P. Let's pick values of P that are between 0 and 1, including 1. So if P is 1, you get this series. If P is a half, you get that series, and so on and so forth. So if P is here, we know the series diverge, which means this type of series will all diverge. And how many are there? There are infinitely many. Why? Because there are infinitely many P's between 0 and 1. So I already know that there are infinitely many series that diverge. Similarly, if P is more than 1, let's say the sum of 1 over n squared, or 1 over n to the 3 halves, let's say P is 3 halves, so it's n root n, or P equals 6, so 1 over n to the 6th. And these are just examples. There are infinitely many series that converge. So I already know that there are infinitely many series that converge, and there are infinitely many series that diverge. Why is this helpful? Because of this. So you can use so many series. These are at your disposal. Put these in your toolbox, right? Put these two in your toolbox, and you can always use them for the direct comparison test, if appropriate. Sometimes you can't use them, and you have to resort to other type of series. But you already know that there are many series called P series that you can use the direct comparison test for and prove other series converge or diverge. All right? I hope this was helpful, and I will see you next time.